Hello everyone. So today let's solve the problem centroids, right? So this was asked in the AIM Tech Round 3 for the division 2, right? So you can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem, right? So let's see what the question states here. So um, we are having a tree with n vertices. We are having a tree with n vertices, right? A vertex is a centroid, a individual vertex when we consider, right? A vertex is a centroid if, let me write this one, just give me a second here. A vertex is a centroid if every connected component after removing it has a size less than or equal to n by 2, right? Less than or equal to n by 2. Just remember this. This is one of the criteria that they have given in the question. This is very important. Let me read this one out loud. Again, just listen to this. A tree with n vertices. We are having a tree with n vertices. A vertex is a centroid if every connected component after removing it has the size less than or equal to n by 2, right? Size less than or equal to n by 2, right? So we may perform at most one edge replacement, nothing but removing one edge and adding another so that the graph remains a tree, right? So this we can do, right? So for every vertex, we have to output one if it can become a centroid after less than or equal to one edge replacement, right? Else we have to this one output 0, right? So just remember this. Let me read this one out loud. Just listen to this carefully. We are having a tree with n vertices, right? A vertex is a centroid if every connected component after removing it has a size less than or equal to n by 2, right? So we may perform at most one edge replacement, nothing but removing one edge and adding another, so the graph remains a tree, right? For every vertex, we have to output one if it can become a centroid after less than or equal to one edge replacement. Else, we have to output 0. Else we have to output 0. That's what we need to do. So this is the question, basically simple one, right? So now let's do one thing. See here, we have been given 3 and we have edge 1 2 and 2 3, basically 3 nodes, right? N is 3 here. 1 2 3 we have 3 nodes we have here, right? So 1 2 as well as the 3. So these are the edges 1 2 and 2 3. The output that we need to get here is triple one. Same goes with the example 5 as example 2 as well, or the input 2 as well. See, so we have this one, 5 nodes here, 1 2 3 4 5. You can clearly see here, right? 1 2 3 we have here, 4 we have here, 5 here, right? So total 4 edges we have, 1 to 2, 1 to 3, 1 to 4, and 1 to 5. The output that we need to get here is 1 followed by 4 zeros, right? So this is about the input output as well as the question. Question is very simple. We have the understanding on the input and output as well, input output as well. Now let's do one thing. Let's discuss the approach followed by the complexities, and then let's write the code. As usual, let's discuss the approach first. So here I have considered the same first example that they have given in the question. N we have been given 3 here, nothing but the number of nodes. Number of nodes we have 3. See here, 1, 2, 3. These are the edges basically, right? So we can just consider here 1 to 2 and 2 to 3, right? So this is the edge 1 to 2 and 2 to 3, left skewed or right skewed, you can consider as well. So the output that we need to get here is triple one, right? So we will be making use of the DFS to solve this particular problem. Just remember this, we'll be making use of the DFS to solve this particular problem. Let's move on with the step-by-step explanation here. So first we have been given n equals to 3. M is nothing but the n by 2. N by 2 we do this one point something we get. So we will be going with a 1 basically, right? So a centroid must leave all the components less than or equal to 1 after the deletion accordingly with the input that we are considering. So we have considered the first example that they have given in the example for the approach, right? So this is for the vertex, this one, what do we call? One second. Mm, yeah. So a centroid must leave all the components less than or equal to 1 after deletion, right? So this one we know from the question as well. So removing vertex 2, removing the vertex 2, right? So we have actually 1 to 2 and 2 to 3, right? For the example 1 to 2 and 2 to 3, this edge. So removing the vertex 2 gives the component, suppose if we remove this one, gives the component, we have removed this one, 1 as well as the 3 basically. right? 1 and 3, right? So if we remove this one, 1, 2 and 3. Suppose if we remove this one, we get 1 and we get 3, right? So removing vertex 2 gives components 1 and 3, sizes 1 and 1, right? Size both are of the size 1 and 1 basically. So this is already okay. So output will be quite obviously 1 here, right? So both are of the sizes 1 and 1, right? So it has to be less than or equal to 1 after deletion. So we have removed 2. Now we have 1 and 3 components which are different and both are having the size 1 and 1 respectively. So this is accepted. So we have the output 1. Now let's move on with the vertex 1. So removing vertex 1, see here, we have 1, 2, 3. Removing the vertex 1. Now we are removing this one, right? Removing the vertex 1 gives the component 2, 3. So this one we can consider at once. So this is still connected, which is of the size greater than 1. So size 2 here. We have got size 2, right? So this is connected. And this is not centroid currently, right? So but we can do one edge replacement here. Remove the edge 2, 3 and add the edge 1, 3, right? And add 1 to 3 basically. New tree becomes the star with the center 1. Star with the center 1, right? So this one we can do. So removing results in 2 and 3. So suppose we remove 2, this one, and we add 1. This is similar to 1 itself, right? So this is similar to the vertex 2 that we previously considered. These two are different, right? So this becomes basically 2 and 3, which are of sizes 1 and 1. Now centroid output is 1 basically, right? So now we can consider output 1, right? So this is for the vertex 1. Now let's move on with the vertex 3. This is symmetric to the vertex 1 itself. So output remains same. You can just check here, right? So if we remove this one vertex 3, we get 1, 2. So this is symmetric to the vertex 1. We can directly consider 1, 1, right? So this is fine. Final output that we got here is 1, 1 and 1 respectively, right? So final output that we got here is 1, 1 and 1 respectively, right? Which is similar or which is equivalent to the output that they have given for the example 1 within the question. So our approach works absolutely correct here. As we are completely familiar with the approach, let's move on with the complexities part. So the time complexity would be here because of n. So why the time complexity here would be because of n? Because each edge or the node that we are considering is visited a constant number of times here across DFS1 and DFS2. So we will be making use of the two DFS helper methods. So that you will come to know when we write the code, right? So we can just make use of the DFS1 and 2 helper methods and we can go with that, right? So overall time complexity would lead to big of n. So what would be the space complexity? Big of n as well, because we'll be going with the adjacency list and arrays. We'll be considering size array f1, f2, p, hs, max as well as the answer, which requires linear memory. So this one overall space complexity would lead to big of n as well. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of 1 and big of 1 big of n and big of n respectively. So now as we are completely familiar with the complexities and the approach, we are good to write the code. Let's start writing the code. Now let's start writing the code, right? So first thing, we'll be making use of the different utilities. So I'll just go with java.util.start, right? Let's go with a class actually, main as usual. Can give any class name that's relevant to the question, right? So first, let's go with the maximum array size, right? So I'll just go with here static final int n equals, let me go with the value 40010, right? So this is fine. So next, let's go with the number of vertices, initializing the number of, let's initialize number of vertices as well as the floor. That is nothing but n by 2, right? So let's go with the variables n and m for this. Static int n comma m, right? So now as I've said, we'll be going with the answer variable size. HS is nothing but the child of X with a maximum subtree size, and F1 and F2 of X. F1 of X and F2 of X. F1 of X is nothing but the largest good value, and F2 of X is the second largest such value, right? So we'll also be going with the P of X, nothing but the child that contributed to the F1 of X, and this one MX of X, nothing but best value coming from the parent side, right? when rerouting. Basically, these are the things that will be initializing. Let's do that very quickly, man. Just go with static here. Int answer equals new int of size n. Right. Next, let me go with the static here. Int size equals new int of size n. Doing the same thing for all the variables. So let me copy this one. So this is for the after size hs f1 f2 p as well as the this one best value coming from the parent side when rerouting, right? Nothing but max here. Let me change the variable names here. Size is fine, sz. So hs f1 f2, this is also fine, and then p finally. So this is fine. Yep. Let me come out of this one entirely, or we have one more thing, right? So we have to go with the adjacency lists as well. I completely forgot this one. This one has to be static array list, the type integer. This is fine. Let me consider the variable e. Let me go with array list here. Yeah, let me give which is of the type integer basically. This has to be empty array. And let me go with new array list, right? Of size n for this one as well. Right, so we are done with the initialization part. Now, as I've said, as we had discussed earlier, that we will be going with a 2 DFS, right? So first, let's go with the first DFS. Why we'll be going with the first DFS? Let me tell you. So we have to compute the subtree sizes and best bad component sizes that is inside the subtrees. So that we will be doing within the first DFS. So let's start writing the code. I'll just go with the static here. Void DFS1. This is fine. Let me go with the parameters x as well as the fa, right? So within this one, within the helper method DFS1, let's initially go with the subtree size of x counts itself, right? So this one will be size of x equals 1, right? So this is fine. Now let's go with a for loop. So let's iterate all the neighbors y of x. So this one will be int y e of x, right? So this one within the for loop, let me go with the if condition. We have to skip the parent to avoid going back, right? So I'll just go with if y equals fa. So I'll just go with the continue, right? So this is fine. Now let's recurse into the child y. So this one will be dfs 1 of y comma x. We are just going with the recursion, right? So this is fine. We are just recursing into the child y. Next, after recursion, so after recursing actually, we have to add the child subtree size to the current node subtree size. So this is simple, man. We have considered size of x equals size of x plus size of y. Simple, right? So now let's move on with the further things, right? So we know that w is equivalent to the this one. What do we call child subtree size when greater than m, right? Then we care about the largest bad place inside that, right? So otherwise the whole child subtree size is itself is the candidate. So that we know from the approach basically. We can just write it in this way. W equals size of y. If it is greater than m, then let me go with the f1 of y. That is the reason we have considered f1 and f2, right? So f1 of y. Sorry, I have already written this. Yeah, f1 of y. Else we'll be going with the size of y, right? So this is fine, man. Now let's do one thing. Yeah, let's track the heavy child, meaning the child with the largest subtree size, right? So this one, if size of y, if it is greater than size of this one, hs of x, this is also fine. Yeah. Now what should I do? I'll just go with the hs of x. Let me assign this one to the y. Yep, this is fine. Now let's do one thing. We have to maintain the top two maximum w values among the children. F1 of x has to be greater than or equal to f2 of x. Yeah, right. So let's write the simple if condition. Let me show this one step by step. If w greater than f1 of x, then we have to demote the previous max to the second max, right? So second max is nothing but f2 of x. We have to assign this one to the f1 of x. Let's set the new max as well as let's record which child gave us f1 basically. Let's do these two things. F1 of x. Let me assign this one to w. Also p of x. Let me assign this one to the y. This is fine. Yeah. Else what we will do? Else, if w greater than f2 of x. If w greater than f2 of x, then let's update the second max if needed, right? So this one will be f2 of x equals w, right? So this is fine. Let me come out of this one entirely. Yeah. Now we are done with the first DFS. So let's go with the second DFS. So now let me explain you why we will be making use of the second DFS first, right? Second DFS. So this is nothing but the rerouting step. So I have said in the first this one DFS, if you remember correctly. So what did I say? First DFS is for computing the subtree sizes and the best bad component inside this one. Best bad component sizes inside the subtrees, right? So the second one we have to reroute. We have to reroute basically. This is nothing but the rerouting step. We will be computing the answer for each node using the information from the children, right? And also the parent side. And also the parent side. That's what we will be doing within the DFS2. Let's do this one very quickly, man. Just give me a second here. Yeah. Let me go with your static. Scroll this one up. Just give me a second. Yeah. Static void DFS2 here. So let me go with the parameters x as well as fa. This is fine. Within these parameters, basically, I'll just go with Boolean. Okay. And let me go with a simple if condition here. If size of hs of x, this is fine. If it is greater than m, let me go with let's assign this one to size of hs of x. This is fine. Yeah, minus f1 of x basically less than or equal to right. Yep. Now let's go with else if uh, else if the parent side component n minus size of x, whatever we have considering, right? Whatever we have considered basically, if it exceeds m, then we must check whether by cutting somewhere in the parent side using the mx of x, right, that we have made use of the variable name. So we can make that component less than or equal to m or not, that we have to check. I'll just go with here n minus size of x. If it is greater than m, then let me assign okay to this one, n minus size of uh, x basically. This is fine. I'll just go with minus mx of x. I hope this is fine. This is less than or equal to m or not, that we need to check. This is fine. Else we will set okay true, boolean value true. This is fine. Yep. After this step, we have to set the result for the node x. So we are going with the result variable ans, right? Answer of x. If it is equivalent to okay, then we have to display 1, else 0. This we know this from the question itself, right? They have directly said this one in the question. Now the next step is for each child y, we have to compute mx of y, right? So let's go with the iteration part. Int y of e of x. Yeah. Let's write the simple if condition here. If y equals fa, then let's skip, meaning I'll just go with the continue keyword here. Then let's do one thing. I'll just go with mx of y which is equivalent to the mat dot max n minus size of this one. What do we call? Size of x it has to be actually. This has to be within the arrays. Oh, sorry. What did I do? Yeah. One second. Yeah. This one has to be size of x. If it is greater than m, then we have to display mx of x. Else, we have to go with n minus size of x basically, comma, p of x. If it is not equal to y, then if it is true, we have to display f1 of x, right? F1 of x, or yeah, f1 of x. Else we have to display f2 of x. So this is fine, I believe, right? So we are done with this part. Now, hmm, now what we need to do here? Hmm, finally, we have to recurse into the child y with a component mx of y, right? So I can just write it in this way. We are recursing dfs2 of y comma x. So this is fine, I believe. Let me come out of this one entire lemon. So we are left with the main method only, right? So we have performed two DFS here, DFS1 and DFS2. I have explained that one clearly. So let's go with the main method basically. So I'll just go with here. Don't have to involve anything here. So this is fine. So now let's go with the scanner. Scanner is enough for this particular problem. I'll just go with the variable sc here, new scanner of system dot in, right? So what we are doing here, we are just going with a so the scanner is fast enough here, right, for the input output, right? So this is fine, man. Next, let we have to read n and m, right? So we have to read the number of nodes. We have to go with the threshold for the centroid check, nothing but floor of n by 2, right? First, let's read the number of nodes, nothing but n in our case. So let's go with the scanner dot next int here. This is fine. Let's go with the threshold for the centroid check. M equals n by 2. This is how we calculated, if you remember the approach basically, right? So this is fine. Now let's go with the for loop. We have to initialize the adjacency lists as well, right? So I'll just go with for I equals 0, I less than, we have considered capital N, right? I plus plus. So this one E of I equals new array list. This is fine. Yeah, we are just we have successfully initialized the adjacency list. Now let's go with a one more for loop here. For int I equals 1, I less than n, I plus plus. So this is fine. So within the for loop, what we will do, let's read an edge endpoints, right? So this one int x equals scanner dot next int. So let's go with the next int. So this is fine. Also, let's go with the y here, scanner dot next int again. So we are just reading an edge endpoints. Now let's add y to x's adjacency and add x to the y's adjacency, right? So this is this one undirected. We know this one, right? So this one is e of x dot add of y. This is because of the adjacency list. So this is fine. This is common, man. We have to type this one anyway. Add of. Yep. Now let me come out of this one entirely. So now first let's run the DFS1. So we have to run the first DFS as well as the second DFS. That is the reason we have written two helper methods DFS1 and DFS2, right? So let's run the DFS first DFS from the node 1. Also let's run the second DFS to compute the answer by rerouting these two things, right? So I'll just go with here DFS1. So this one will be 1 comma 0. Again the same goes with DFS2 as well. DFS2 1 comma. Right, after successfully running both the DFS that we have written, now we have to build the output efficiently. For that, I'll be going with a string builder here. Let me consider the variable name SB, create instance of it, string builder Yeah, we are just building the output efficiently. Now let's append the answers from 1 to n. So I'll just go with the for loop here. I equals 1, I less than or equal to n. Let me increment the I. So this one will be string builder dot append. This is fine. So this will be iterated value of the answers. This is fine. Let's append the empty space basically. We are just appending the answers from 1 to n, right? So finally, let's go with the this one, system out println. So let me give system out println of SB is this one string builder variable, right? So we are just printing the results on single line. So we are not printing the answer in the next line, right? In the single line we have to print. So let me pass SB. This is fine, man. Yeah, this is it for the code. So before checking the code with the different inputs, so let me copy paste the signature starter template. So let me come here, let me paste this one, right? I'll just come to the question. So let me copy this one, the output that we need to get here is triple one. Let's check the same here. Error, not a statement. Why? What's wrong here? Line number 75. 75, 75. Oh yeah, this one has to be parenthesis actually, not the square bracket. Right. So let me run this one again. Yeah, we are getting the output triple one, which is absolutely correct, right? So you can just ignore the warning, or you can just add suppressed this one. What do we call? Mm, something suppressed. This one you can add, right? So something unchecked that you can add. That error will go away. So this works fine with the code forces environment. We don't have to worry about that. So I'll just copy this one followed by the four zeros we have to get. Let's check the same. Yeah, one followed by four zeros. We are getting the correct output. So let me copy this one entirely. I'll come here. Let me hit the submit button. Yeah. So let me paste the code and also I'll just come here. Let me copy this one. This is 709, right? So I'll just give here 709 and paste the question here, right? So let me hit the submit button. I hope it works for all the test cases, man. Let's see. Let's wait for some time. Test one. Let's wait. How many test cases we are having, man? Oh, this is so slow. Let's wait for some time. Still running on the test 61 actually. This is fine. much time this will take, man. I have made use of the scanner, right? At least I would have rather than the custom this one fast this one input, I would have made use of this one buffer data in the print data. So here you can clearly see, man, we got accepted, right? So uh, what do we call here? In the toast, it is showing accepted, and also the verdict that we got here as accepted, right? So here we have made use of the pure DFS to solve this particular problem. We have went with the two DFS to solve this particular problem. Why we have made use of how we have made use of, you have already seen. I have explained this one step by step, right? So we have returned two helper methods DFS1 and 2, and then finally we have made use of those DFS1 and 2 helper methods within the main method, right? So this is it for the basically centroids question. So I hope the solution part is completely clear along with the approach as well as the complexities. For now, this is it. Thanks for watching, guys.